The Big Bang Theory, long held as the leading explanation for the origin of the universe, is currently facing new challenges as a result of remarkable discoveries made by the James Webb Space Telescope, JWST. This powerful telescope, launched with the goal of observing the early universe with unprecedented detail, has provided groundbreaking insights that have the potential to dramatically reshape our understanding of how the cosmos came into existence, how it has evolved over time, and what its ultimate fate might be. One of the most significant developments from this mission involves a recent image captured by JWST that has generated widespread discussion and debate among scientists and astronomers. The image is more than just another beautiful glimpse into space. It contains compelling evidence that has surprised the scientific community and helped address long-standing debates about the very nature and structure of the universe. This visually stunning discovery is not merely an astronomical curiosity. It carries the potential to revolutionize our understanding of the cosmos. The latest image taken by the JWST challenges some of the most fundamental assumptions we've held about space, especially concerning the age of the universe and the rate at which it is expanding. These are not new questions. They have puzzled scientists for generations, prompting decades of research, experimentation, and theorizing. Over time, numerous hypotheses have been proposed in an effort to arrive at definitive answers. Cosmologists, those who study the origin and development of the universe, dedicate their careers to understanding where the universe came from, how it operates, how it has changed over billions of years, and how it might one day come to an end. During the past century, this field has seen tremendous advancements, with one of the most significant being the development and acceptance of the Big Bang Theory. According to this theory, which remains the most widely endorsed explanation for the universe's origins, the cosmos began approximately 13.8 billion years ago from an extremely hot, dense singularity. Since that event, the universe has been expanding. A key part of understanding this expansion is calculating the Hubble constant, a value that quantifies the rate at which the universe is growing. However, determining the Hubble constant has proven to be far from straightforward. Scientists use two primary methods. One based on local measurements, such as observing stars and galaxies close to us, and the other using observations of the early universe, particularly data from the cosmic microwave background (CMB), a remnant of the Big Bang itself. Unfortunately, these two methods often yield different results, leading to what's known as the Hubble tension. To measure the Hubble constant locally, astronomers rely on specific celestial objects like stars and type Ia supernovae. These serve as standard candles due to their predictable brightness. By comparing their intrinsic luminosity with how bright they appear from Earth, astronomers can estimate their distance and, in turn, calculate the rate of cosmic expansion. However, the universe does not expand uniformly. This unevenness makes it even more difficult to pinpoint a consistent, exact value for the Hubble constant. Meanwhile, the alternative approach involves studying the early universe through the CMB, radiation left over from a time when the universe was only about 380,000 years old. First detected in the 1960s, the CMB has provided invaluable information about the age, shape, and rate of expansion of the cosmos. By analyzing the tiny fluctuations in the CMB's temperature and polarization, cosmologists can infer the universe's early behavior. Yet, a major issue has emerged. The expansion rate derived from local measurements consistently appears faster than that inferred from CMB data. This persistent mismatch suggests either an incomplete understanding of fundamental physics or potential errors in one or both measurement techniques. Scientists around the globe have been working tirelessly to solve this mystery, as it could point to a major paradigm shift in cosmology. The James Webb Space Telescope, with its revolutionary technology, was expected to help settle this dispute. Thanks to its ability to peer deeper into space and farther back in time than any previous telescope, JWST allows scientists to detect celestial bodies and phenomena that were previously beyond our reach. Initially, researchers were optimistic that JWST's precise observations would help refine the calculation of the Hubble constant and provide clarity. Instead, the data it has delivered has only intensified the puzzle. The findings introduced new inconsistencies that challenge existing cosmological models and force scientists to reconsider long-held assumptions about the structure and behavior of the universe. This has led to growing speculation that the universe might contain previously undiscovered particles or forces, or perhaps our entire framework for understanding space needs a fundamental overhaul. Some experts have even suggested the need to reevaluate the concept of dark energy, a mysterious force believed to be responsible for the accelerating expansion of the universe. Scientific understanding has always evolved in response to new data. A notable example is the discovery of the cosmic microwave background radiation in 1965, which provided strong support for the Big Bang theory and challenged prior beliefs that the universe would expand forever at a constant rate. Later, in the late 1990s, observations of distant supernovae revealed that the universe's expansion is not slowing down but accelerating. This was attributed to the presence of dark energy, a discovery that reshaped our entire understanding of cosmology. Each discovery like this forces scientists to test whether existing theories can still explain the data, or whether new frameworks are required. One of the most captivating aspects of the current cosmological debate is the concept of Hubble tension. This refers to the discrepancy between different measurements of the universe's expansion rate. The issue is closely connected to the distribution of matter in space, since differences in how matter is spread out influence the large-scale structure of the universe. While some regions are densely packed with galaxies, others are comparatively empty. To study this, scientists use methods like gravitational lensing, where massive objects like galaxy clusters bend and magnify the light from more distant sources. This phenomenon allows researchers to detect and map dark matter, an invisible substance that doesn't emit or reflect light but exerts gravitational influence. Gravitational lensing and continued analysis of the cosmic microwave background provide additional clues to understanding these cosmic irregularities. The light from the CMB has traveled for roughly 13.8 billion years, carrying with it crucial information about the early universe. Yet, there remains a contradiction. The large-scale distribution of matter seen today does not match the uniformity indicated by the CMB data. This implies that there may be hidden factors influencing the development and structure of the cosmos. The apparent non-uniform distribution of gravitational forces suggests that the universe may have been more homogeneous in its infancy than current observations suggest. This inconsistency has prompted scientists to revisit theories about dark matter and its role in cosmic evolution. In an effort to resolve these inconsistencies, a research team led by Dr. Rhee and his colleagues used JWST to examine whether earlier telescopic observations contained measurement errors. Their work, however, confirmed the existence of these discrepancies, reinforcing the idea that a deeper flaw might lie within our current understanding of the cosmos. In an interview with a major astronomical magazine, Rhee expressed his concern that somewhere between the conflicting data lies a crucial gap in knowledge. The telescope's extraordinary ability to produce crystal-clear and detailed images has enabled astronomers to study cosmic distances with a level of precision never before achieved. But instead of resolving uncertainties, this precision has uncovered more questions, especially regarding the mysterious forces of dark matter and dark energy. Both of these entities remain among the greatest unsolved mysteries in physics. They are thought to make up the majority of the universe's mass-energy content, yet scientists still don't fully understand what they are. Traditionally, black holes were considered prime candidates for explaining gravitational anomalies, but current findings suggest that dark matter and dark energy may have far more complex roles in shaping the cosmos than previously imagined. As evidence continues to grow, it is becoming increasingly clear that current models may need revision because they fail to fully account for the intricate processes driving cosmic expansion. JWST's discoveries are a powerful reminder of the ever-evolving nature of science. Each new observation forces experts to re-examine assumptions, refine theories, and consider entirely new perspectives. These developments underscore the importance of continued research and the development of even more advanced observational technologies. As telescopes become more powerful and techniques more refined, the hope remains that these mysteries will eventually be solved. Until then, the pursuit of understanding the fundamental forces that govern the universe remains one of the most exciting and intellectually challenging endeavors in modern science. What makes the JWST's findings particularly striking is that instead of solving long-standing issues, they have unveiled new uncertainties. Astronomers initially hoped the telescope would settle debates surrounding the Big Bang theory, the expansion rate of the universe, and the roles of dark matter and dark energy. Instead, the telescope has offered new data that challenges core principles of cosmology. For example, it has revealed distant galaxies that appear more developed than they should be, based on their age. According to the Big Bang model, the earliest galaxies should be small and relatively simple. Over time, they grow and become more complex. But JWST has identified massive, mature galaxies that seem to have formed just a few 100 million years after the Big Bang, contradicting established models. This raises profound questions. Were the conditions of the early universe different than we believed? Was the matter distributed less uniformly, allowing some regions to develop faster? Or are there completely unknown physical processes at work that accelerate cosmic evolution? These are the types of questions that now drive modern cosmological research. Some researchers are even proposing modifications to the standard model of cosmology, including theories involving new forms of matter or interactions not yet identified by current physics. The implications of these discoveries go beyond just astronomy. They may influence the broader field of fundamental physics. If our models of dark matter and dark energy are wrong or incomplete, scientists may need to construct entirely new theories. This could lead to breakthroughs in our understanding of gravity, particle physics, and the very fabric of spacetime itself. In many ways, JWST